At this exact moment, humanity is connected by a web of technology more complex and fragile than at any other point in our history. The year 2026 represents the absolute peak of our global communication network. Across North America, the joint hosting of the World Cup in the United States, Canada, and Mexico has turned the continent into the focal point of global attention. This is not merely a sporting event. It is a demonstration of our ultimate technological dependency. Billions of people across every continent are watching the same high-definition broadcast, relying on a system of satellites, submarine cables, and data centers that operates without interruption. If you feel the weight of this cosmic fragility and want to explore the deepest mysteries of the universe with us, leave a like and subscribe to Deep Space Signal. Let us continue the journey together. The scale of this connection is unprecedented. To transmit a live 4 kHz signal to billions of screens simultaneously requires a massive orbital array. Dozens of geostationary satellites position themselves in narrow orbital lanes, relaying signals from the stadiums to regional networks. On the ground, the cities hosting these matches are operating at the absolute limit of their physical infrastructure. During the height of the summer heat, local power grids are pushed to their thresholds. Air conditioning systems, public transit networks, security arrays, and the massive stadiums themselves consume the electrical output of entire cities. This system is designed for efficiency, not resilience. To maintain this level of connection, the power grids must operate in a state of continuous balance. High-voltage transmission lines carry electricity across thousands of miles, synchronized to the fraction of a second. The data networks rely on cloud servers that verify transactions, route internet traffic, and process payment systems in real time. Millions of international tourists are traveling across the host nations, using mobile applications to navigate transit, access digital tickets, and pay for services with credit cards. They operate under the assumption that the digital layer of society is a permanent feature of their environment. They do not realize that this entire network is stretched tight, operating with almost no safety margin, completely vulnerable to external shocks. The synchronization of the transmission lines is a complex engineering challenge, as the alternating current must be maintained at a constant frequency of 60 Hz across the entire eastern interconnection. Even a minor deviation in frequency, caused by an unexpected surge in demand or a sudden drop in generation, can trigger automatic safety switches, disconnecting portions of the grid. During the summer heat, the transmission lines expand and sag, reducing their carrying capacity and leaving the system vulnerable to cascading failures. The power plants, operating at maximum capacity, rely on these lines to deliver electricity to the urban centers where the matches are hosted, creating a highly centralized and vulnerable energy network. At the same time, the server farms that manage cloud-based services are consuming immense amounts of energy. These facilities process the digital requests of millions of users, verifying credit cards transactions, routing streaming data, and hosting the applications that tourists use to manage their travel schedules. These data centers require a continuous supply of electricity and cooling water to prevent overheating. The entire digital structure is dependent on this physical foundation, which operates in the background, invisible to the users. The reliance on these centralized systems means that a failure in the electrical infrastructure would immediately disable the digital transactions that support modern life, showing that our connection is limited by the stability of our machines. In orbit, the geostationary communication satellites are positioned in a narrow band above the equator, approximately 22,000 miles above the surface. This specific orbit allows them to rotate at the same speed as the Earth, remaining fixed above a single point on the ground. This positioning is essential for maintaining a continuous connection with satellite dishes on the ground, which do not need to track a moving target. However, this orbital environment is exposed to the solar wind and cosmic radiation, relying on physical shields and magnetic field deflectors to protect their delicate electronics from the energetic particles of space, representing a fragile link in the communication network. The vulnerability of this connected network is a fundamental feature of our modern design. By concentrating our communication channels and energy grids into centralized nodes, we have maximized efficiency at the expense of systemic safety, creating a system that can be compromised by a single event in our orbital environment. 93 million miles away, the source of our energy is preparing a major disruption. The Sun operates on an 11-year magnetic cycle, during which its activity rises and falls. In the summer of 2026, the solar cycle is at its maximum, and the solar surface is covered in massive active regions. These are areas of intense magnetic field concentration, visible as dark sunspots. One of these regions, a massive magnetic structure spanning several times the diameter of the Earth, has accumulated an immense amount of energy. The magnetic field lines above this region have become twisted and stressed, store energy like a compressed spring. The trigger occurs in a fraction of a second. A process known as magnetic reconnection takes place, where the magnetic field lines snap and configure themselves into a lower energy state. This event releases a burst of energy across the electromagnetic spectrum, generating a powerful X-class solar flare. This flare vents high-energy photons, including X-rays and ultraviolet radiation, which travel outward at the speed of light. At the same time, the magnetic collapse launches a colossal bubble of solar plasma and magnetic fields into space. This is a coronal mass ejection containing billions of tons of charged protons and electrons. This specific eruption is what solar physicists call a Cannibal CME. It occurs when a fast-moving coronal mass ejection is launched shortly after a slower one. As the second wave travels through space, it sweeps up the plasma of the first wave, merging into a single, highly magnetized cloud of charged particles. This combined wave travels at speeds exceeding 2,000 kilometers per second. It is aligned with the orbit of the Earth, creating a direct path of collision. The space weather monitoring satellites orbiting at the Lagrangian point L1 detect the eruption, transmitting warning data to terrestrial stations, but the arrival of the energetic particles is a physical certainty written in the mechanics of solar physics. The solar dynamo, the physical process that generates the sun's magnetic field, operates deep inside the convection zone. As the plasma rotates at different speeds at different latitudes, the magnetic field lines are stretched and wrapped around the solar interior. This process concentrates magnetic flux, creating the sunspots that mark the surface. During the peak of the solar cycle, these active regions are highly complex, containing fields of opposite polarity in close proximity. This complexity increases the probability of magnetic reconnection events, which can release energy equivalent to millions of hydrogen bombs in a matter of minutes. The resulting coronal mass ejection is not a simple cloud of gas, but a highly structured magnetic bottle containing billions of tons of ionized hydrogen and helium. The magnetic field of the CME is twisted, and its orientation relative to Earth's magnetic field determines the severity of the storm. If the solar magnetic field points southward, it will align opposite to Earth's northward pointing field. This alignment allows the two fields to merge, opening a channel for the solar wind energy to enter Earth's magnetosphere. A Cannibal CME is especially dangerous because the merging of the two plasma clouds increases the magnetic field strength and the density of the particles, creating a highly compressed shock wave that travels through the solar system. The timing of this eruption is a critical factor. As the Earth rotates, different regions are exposed to the sunward side of the magnetosphere. The arrival of the shock wave during a period of high electrical demand, such as the afternoon of the final match, maximizes the potential disruption. The space weather prediction models run on terrestrial supercomputers attempt to calculate the arrival time by tracking the expansion of the CME through satellite imagery. However, the interactions between the solar wind and the CME are complex, leaving an uncertainty of several hours in the forecast, which limits the ability of grid operators to prepare for the impact. The tracking of this coronal mass ejection becomes the primary focus of space weather observatories around the globe. As the magnetized plasma travels through the solar system, it alters the local solar wind parameters, generating precursor waves that provide critical data for our prediction models, warning us of the approaching magnetic shock. The first strike from the solar eruption arrives in just over 8 minutes. The high-energy photons from the X-class solar flare reach the Earth, striking the upper layers of the atmosphere. This radiation immediately ionizes the atoms in the ionosphere, particularly the D layer, which sits between 50 and 90 kilometers above the surface. Normally, this layer reflects high-frequency radio waves, allowing long-distance communications. Under the impact of the solar flare, the D layer becomes highly conductive, absorbing radio signals instead of reflecting them. This creates a high-frequency radio blackout across the sunlit side of the planet. Commercial flights crossing the oceans lose contact with air traffic control as their primary communication channels are silenced. Marine vessels, emergency networks, and shortwave radio stations experience a sudden drop in signal strength, replaced by static. This is an invisible event, unnoticed by the general public, but for the systems that monitor our skies and oceans, It is the first indicator of an approaching space weather crisis. Meanwhile, the high-energy protons launched by the flare begin to arrive, traveling along the open magnetic field lines near the poles. These particles collide with satellites in high-altitude orbits, including geostationary communication satellites and global positioning networks. The protons penetrate the electronic shielding of these space structures, causing memory upsets, phantom commands, and degradation of solar panels. As the satellites travel through this bath of ionizing radiation, electrostatic charge accumulates on their outer surfaces. This differential charging can trigger electrical discharges inside the delicate circuitry, disabling the systems that route global data streams, showing that our space infrastructure is the first casualty of the solar storm. The ionization of the D layer of the ionosphere is a direct result of photoionization, where high-energy photons split electrons from atmospheric nitrogen and oxygen atoms. The density of free electrons in this layer increases by several orders of magnitude, creating a conductive medium that acts as a physical barrier to radio waves. The radio signals, instead of passing through or reflecting back to the ground, transfer their energy to these free electrons, which then collide with neutral molecules, dissipating the signal as heat. This absorption is most intense in the high-frequency bands used for long-distance communication, creating a total radio blackout. For commercial aviation, this blackout represents a significant operational challenge, especially for flights crossing polar regions. Polar routes rely on high-frequency radio links because satellite coverage is limited at high latitudes. When these links are severed, pilots cannot receive weather updates, route changes, or safety instructions. Aviation safety guidelines require aircraft to divert to lower latitudes or land at the nearest airport if communication is lost for extended periods. This diversion disrupts flight schedules globally, creating congestion at regional airports and separating airlines from their planned routes, illustrating how space weather can alter transportation networks. At high altitudes, the arriving solar protons create a different hazard. These particles, accelerated to relativistic speeds, can penetrate the hulls of spacecraft and satellites. When a proton collides with a silicon chip inside a satellite's computer, it can change the state of a single bit of memory, an event known as a single event upset. This change can trigger software errors, causing the satellite to lose its orientation or disable its communication systems. The differential charging of the satellite's surface, caused by the accumulation of static charge in the solar wind, can also trigger arc discharges, damaging external components and separating the spacecraft from ground control. The impact of these arriving protons represents the beginning of a larger atmospheric transition. As the high-energy particles interact with the polar atmosphere, they create chemical reactions that alter ozone concentrations and increase the conductivity of the lower layers, showing how solar activity influences the physical dynamics of our protective shield. At the exact moment when the World Cup final reaches its peak, with billions of people connected to the live feed, the space weather crisis translates into a terrestrial event. The electrostatic discharges and component failures disable the primary geostationary satellites routing the signal. For billions of viewers watching in homes, bars, and public squares around the world, the screen simply freezes. A second later, the high-definition feed is replaced by a digital error screen or static. The transition is instantaneous, and it occurs globally. The initial response is confusion. Viewers assume it is a local network issue, a minor cable outage, or a temporary software glitch. People check their connections, restart their applications, and wait for the stream to recover. But the signal does not return. In the broadcast control rooms at the stadiums, technicians watch their incoming feeds drop to zero. The telemetry data from the satellites shows that the attitude control systems are offline, preventing the dishes in space from pointing toward their target stations. This is the day the global broadcast dies. The loss of the signal is the first sign for the general public that something is wrong on a global scale. The collective experience of billions of people watching the same event is shattered, replaced by a quiet void of information. As the minutes pass without recovery, the confusion turns into concern. The absence of information creates an immediate demand for answers, and people turn to their mobile devices to find out what has happened, unaware that the communication systems they rely on are already failing at the structural level. The attitude control systems of communication satellites rely on reaction wheels and magnetic torquers to maintain their orientation relative to Earth. These systems use telemetry data from star trackers and sun sensors to make minor adjustments. keeping the communication antennas pointed toward the ground stations. When the solar proton bombardment disables these sensors or corrupts the attitude control software, the satellite begins to drift in space. Even a deviation of a fraction of a degree is sufficient to disconnect the high-frequency transponders from the ground station, silencing the broadcast. The failure of the transponders occurs at multiple frequencies, affecting both the C-band and Ku-band signals used for television distribution. These signals are received by regional networks and cable operators, who then distribute the feed to millions of households. When the satellite links are severed, the distribution network collapses. The local broadcast stations are left with no incoming feed, and they are forced to display test patterns or static. The loss of the signal is not localized. It occurs across the entire footprint of the disabled satellites, covering entire continents in a silent informational void. The public response to the broadcast failure is marked by a rapid transition from entertainment to anxiety. In public squares and stadiums, the sudden silence of the screens creates an immediate demand for information. People look at their neighbors, check their devices, and attempt to connect with local networks. But the lack of updates increases the confusion. The television broadcast, which had served as a shared experience for millions, becomes a source of isolation. The silence of the screens is a physical reminder of our reliance on a distant orbital infrastructure that we cannot see or repair, highlighting the fragility of our connected culture. This silent transition from normal operations to total satellite failure is a direct consequence of our orbital vulnerability. The loss of these transponders isolates entire regions from the global flow of information, showing that the systems we use to connect our societies are dependent on the quiet conditions of space weather. As the broadcast fails, a secondary crisis develops across the global internet infrastructure. Millions of people attempt to access news websites and social media platforms at the same time to understand the source of the outage. This sudden spike in traffic coincides with the physical failure of key network nodes. The internet is a decentralized network designed to route data around localized failures, but it relies on key routing centers and submarine cables to connect continents. Under the impact of the solar storm, the satellite networks that back up our terrestrial grids are offline. This forces all data traffic onto undersea fiber optic cables. These cables are protected by the ocean, but the terrestrial stations where they connect to land rely on regional power grids and synchronization systems. As the data traffic spikes, the routing servers become overloaded, unable to process the volume of requests. At the same time, GPS timing signals which synchronize the transmission of data packets across the global network are degraded by the ionospheric disturbance. The result is a routing failure of unprecedented scale. Domain name system servers fail to resolve addresses, and routers lose their synchronization, causing data packets to loop and drop out. Cellular networks, which rely on fiber optic backhaul and GPS timing to coordinate calls between towers, begin to fail. For millions of mobile phone users, the signal indicator drops to no service. The pánico silencioso begins as people realize they cannot load a web page, send a message to their families, or call for emergency assistance. The digital layer of society, which had seemed so durable, has collapsed in a matter of minutes. The internet backbone relies on the Border Gateway Protocol to route data across the global network of servers and routers. This protocol dynamically updates routing tables, directing data packets along the fastest available path. When key routing centers and satellite links go offline, the protocol attempts to reroute traffic through the remaining paths. This sudden redirection creates a massive load on the surviving terrestrial routers, which are already struggling to process the spike in traffic from users searching for news. The routing tables become unstable, causing packets to drop and connections to fail. At the same time, the domain name system, which translates domain names into numerical IP addresses, begins to fail. DNS servers rely on constant synchronization to update their records. Without GPS timing signals, which are degraded by the ionospheric disturbance, these servers lose their temporal alignment. The synchronization errors cause DNS lookups to fail, preventing users from accessing websites even if the physical connection is still active. The internet becomes a collection of disconnected segments, unable to communicate across regional boundaries, leaving users isolated from global information systems. Cellular networks are also vulnerable to this synchronization loss. Base stations use GPS clocks to coordinate the timing of radio signals between towers and mobile devices, preventing interference. When the GPS signal is lost, the internal clocks of the towers drift, Within hours, the drift is sufficient to cause signal overlap and call dropouts. The towers lose their connection to the core network, and the mobile devices display the message, "No service." The loss of mobile communication prevents people from contacting emergency services, coordinating transportation, or accessing mobile banking, illustrating how the collapse of the space-based timing grid disables ground communication. This systemic failure of the routing grid highlights the delicate nature of our information backbone. The synchronization of our communication systems requires a constant connection to space-based signals, and any disruption to this timing source immediately ripples through the terrestrial networks, disabling the tools that we use for daily survival. While the data networks are failing, the physical wave of the coronal mass ejection arrives. The magnetized plasma of the Cannibal CME collides with the Earth's magnetosphere, compressing the magnetic shield on the day side and stretching the magnetotail on the night side. This collision initiates a major geomagnetic storm. As the solar magnetic field couples with the Earth's field, it creates rapid fluctuations in the local magnetic environment, particularly in high-latitude regions. According to Faraday's law of induction, a changing magnetic field induces an electric field in any conductor it passes through. The Earth's crust is a conductor, and the geomagnetic storm induces electric fields in the ground. These fields find a path of lower resistance through high-voltage transmission lines, which are grounded at substations over hundreds of miles. This process generates geomagnetically induced currents, or GICs. These are low-frequency direct currents that flow through the transmission lines, entering the neutral grounding wires of large transformers. The arrival of direct currents at a transformer designed for alternating current is catastrophic. The DC current causes the transformer core to saturate magnetically, a process known as half-cycle saturation. This saturation increases the magnetizing current, causing the transformer to consume vast amounts of reactive power. The voltage on the grid drops rapidly, and the transformer begins to heat up internally. The copper windings expand, the insulating paper degrades, and the cooling oil begins to boil. Within minutes, the physical components of the transmission grid are pushed to their thermal limits, setting the stage for a cascading failure of the electrical infrastructure. The physical mechanism of geomagnetic induction is defined by Faraday's law, which states that a time-varying magnetic field will induce an electromotive force in a closed loop. During a geomagnetic storm, the rapid movement of the auroral electrojet, a massive electrical current flowing in the ionosphere, induces electric fields in the Earth's crust. These fields create a potential difference between different regions of the ground. High-voltage transmission lines, which are grounded at substations over long distances, provide a pathway for this potential difference to drive currents through the transmission grid. The geomagnetically induced currents are essentially direct currents with frequencies much lower than the 60 Hz alternating current used by the grid. When these DC currents enter the neutral grounding wire of a transformer, they bias the magnetic flux in the core. During one half of the AC cycle, the flux in the core exceeds the saturation threshold. This half-cycle saturation causes the transformer to consume massive amounts of magnetizing current, leading to severe harmonic distortion in the voltage waveform. The transformer acts as a major sink of reactive power, destabilizing the voltage control systems of the entire grid. The heat generated during saturation is a major threat to the physical integrity of the transformer. The magnetic flux escapes the core and enters the structural steel parts, such as the tank walls and winding clamps, creating eddy currents that raise temperatures rapidly. The cooling oil, designed to transfer heat away from the windings, begins to decompose, producing explosive gases. The paper insulation around the copper windings degrades under the high temperatures, increasing the risk of internal short circuits. If the transformer is not disconnected from the grid immediately, it can suffer catastrophic structural damage, melting the windings and causing physical explosions. The generation of these geomagnetically induced currents is an inevitable consequence of our long-line infrastructure. High-voltage transmission networks act as giant antennas for the electric fields induced in the ground, channeling this energy into the vital components of the grid and creating a physical link between solar activity and terrestrial transformers. The physical consequence of transformer saturation is a cascading blackout. High-voltage transmission lines trip offline to protect themselves from damage, shifting the load onto neighboring lines, which then overload and trip in turn. In a matter of seconds, the power grid of the eastern United States collapses. In the stadium in New Jersey, where 80,000 fans are gathered, the massive floodlights turn off instantly. The stadium systems go dark, and the sound system dies, leaving only the sound of 80,000 people talking in confusion. The stadium is a concrete structure designed for high density, and it relies entirely on electricity to function. The digital turnstiles, emergency doors, and electronic gates lock in place, trapping the crowd inside. The ventilation systems shut down, and the air inside the corridors becomes warm and humid. Outside, the public transit systems, including the subways and commuter trains that carry fans to and from the match, are paralyzed as the third rails lose power. Trains stop in dark tunnels, and passengers are confined to their carriages. This is the concrete trap. The density of modern infrastructure becomes a hazard when the power grid fails. Elevators in high-rise buildings stop between floors, trapping workers in small spaces. Traffic lights go dark, causing gridlock at intersections and preventing emergency vehicles from moving. The systems that manage water pressure, waste disposal, and building access are offline. For the fans in the stadium and the residents of the surrounding cities, the transition from modern convenience to physical confinement is immediate, illustrating the vulnerability of our built environment. The automatic protection systems of the electrical grid are designed to prevent catastrophic equipment damage. When relays detect the voltage fluctuations and harmonic distortion caused by transformer saturation, they trigger circuit breakers to disconnect the affected lines. This protection is necessary to save the transformers, but it removes transmission capacity from the grid. The remaining lines are forced to carry the load, leading to rapid overloads and cascading trips. The entire electrical system collapses in a matter of seconds, dropping cities into darkness. In the New Jersey Stadium, the sudden loss of power disables the massive high-voltage lighting arrays. These lights require several minutes to cool down before they can be restarted, even if backup power is available. The stadium's backup generators are designed to power emergency systems, such as exit signs and fire alarms, but they cannot support the massive electrical load of the main stadium lights or the digital systems. The security cameras, public address systems, and electronic ticket scanners go dark. The crowd is left in darkness with no information or direction from stadium authorities. The transit systems that serve the metropolitan area are also paralyzed. Commuter trains and subway systems rely on high-voltage lines to power their traction systems. When the grid fails, the trains stop immediately, often in dark tunnels between stations or on elevated tracks. The electronic signals that manage train traffic go dark, preventing transit operators from moving trains safely. Passengers are trapped in dark, unventilated carriages with no communication from the train crew. The highways are gridlocked as traffic lights fail, preventing private vehicles and emergency services from navigating the streets, trapping the population in a silent, dark environment. The confinement of the population within these dark concrete structures is a direct result of our centralized design. Our modern buildings and transit networks cannot operate without a constant supply of electricity, and the loss of power immediately alters the safety parameters of our cities, creating immediate hazards for the stranded crowds. As night falls over the paralyzed cities, a visual phenomenon emerges in the sky. The auroral oval, which is normally confined to the polar circles, expands toward the equator under the pressure of the geomagnetic storm. Above the open roof of the New Jersey Stadium, the dark sky begins to glow with a faint crimson-red light. This is not the green aurora typical of high latitudes, but a low-latitude red emission caused by solar wind particles colliding with atomic oxygen at high altitudes, between 200 and 400 kilometers. The red curtains of light stretch across the horizon, moving in response to the changing magnetic fields. For the crowd trapped in the dark stadium and the residents of the dark cities, the sight is both beautiful and terrifying. It is a visual confirmation that the environment has changed, a sign that the solar storm has bypassed the planet's magnetic shield. The crimson sky provides a faint, natural illumination, casting long shadows across the concrete structures. At the same time, the mobile phones that people are holding begin to lose their charge. Without network signals, the devices increase their transmitter power to maximum in an attempt to connect with towers, draining their batteries in a matter of hours. The screens flicker and go dark, removing the only remaining source of light and communication for the crowd. The stadium is left in darkness, illuminated only by the red glow of the aurora. The silence is broken only by the sound of the wind. As the reality of the situation begins to settle over the stranded population, The red aurora observed during extreme geomagnetic storms is caused by the emission of light from atomic oxygen in the upper atmosphere. When energetic electrons from the solar wind collide with oxygen atoms at altitudes above 200 kilometers, they excite the atoms to a higher energy state. As the oxygen atoms return to their ground state, they release photons with a wavelength of 630 nanometers, producing a red glow. This process requires low atmospheric density to prevent the excited atoms from losing their energy through collisions before they can emit light, which is why the red aurora is confined to high altitudes. During a supersolar storm, this auroral display moves toward the equator, appearing in regions that never witness polar lights. The red curtains of light move slowly across the sky, changing shape as the Earth's magnetic field lines twist and deform under the impact of the coronal mass ejection. This visual display is a physical demonstration of the solar wind energy interacting with the atmosphere, providing a natural light source that illuminates the dark cities. The eerie red glow replaces the artificial light of the metropolitan areas, creating a silent visual backdrop to the technological collapse. Meanwhile, the mobile devices held by the stranded population are rapidly losing power. In an attempt to connect with towers that are offline, the devices increase their transmitter power, drawing energy from the batteries at an accelerated rate. The screens flicker and go dark, removing the only source of light and communication for the crowd. The silence in the stadium is a physical experience, broken only by the sound of the crowd and the wind. The absence of artificial light forces people to rely on the faint red glow of the aurora to navigate the concrete structure, highlighting the sudden return to a pre-industrial state. The red auroral glow remains a silent indicator of the atmospheric storm. As the excited oxygen atoms continue to emit light, they trace the boundaries of our compromised magnetic shield, providing a visual marker of the solar wind energy entering the atmosphere and reminding us of the physical limits of our environmental security. The scale of the crisis becomes clear when we examine the situation of the international tourists who have traveled to the host nations. Millions of people from all over the world are suddenly stranded in foreign cities. The aviation system is paralyzed. Airplanes cannot fly without GPS navigation, and air traffic control centers require electrical power and communication links to coordinate flights. Airports are closed and commercial aircraft are grounded on tarmacs, unable to take off. The loss of the global positioning system is a critical factor in this paralysis. The GPS satellite signals must pass through the ionized ionosphere to reach receivers on the ground. During a geomagnetic storm, the variations in electron density distort the signal paths, causing positioning errors or complete signal loss. For commercial flights, this represents a safety hazard that prevents operations. Pilots must land at the nearest available runway, and airports become congested with grounded planes and stranded passengers. The international tourists are caught in this gridlock. They cannot check flight statuses, reschedule departures, or contact their embassies. The airport terminals become crowded transit camps, with families sleeping on the floor next to piles of luggage. The language barrier becomes a major obstacle. As travelers struggle to understand instructions from local airport staff, the absence of communication links means they cannot inform their families at home that they are safe. They are trapped in a country whose systems have ceased to function with no way to return home. The GPS system relies on a constellation of satellites in medium Earth orbit, transmitting high-frequency radio signals that carry time and position data. These signals must pass through the ionosphere to reach receivers on the ground. During a geomagnetic storm, the variations in electron density create scintillation, a process that distorts the phase and amplitude of the radio waves. This distortion causes positioning errors in GPS receivers, or prevents them from locking onto the satellites, rendering the system useless for navigation. For commercial aviation, the loss of GPS is a critical safety issue. Modern aircraft rely on satellite navigation for routing, landing approaches, and terrain avoidance. While airplanes possess backup inertial navigation systems, these systems drift over time and require GPS corrections to remain accurate. When the GPS signal is lost, aviation safety regulations require aircraft to remain grounded or divert to the nearest airport. Air traffic controllers, losing their primary radar and communication networks, cannot coordinate flights safely, forcing a complete ground stop of all commercial traffic. The airport terminals become congested zones of stranded travelers. The emergency generators at the airports are designed to power critical systems, such as runway lights and safety alarms, but they cannot support the heating, ventilation, and passenger information systems. The terminals become warm, dark, and crowded, with passengers waiting for information that cannot be delivered. The international tourists, having no local housing or transportation options, are forced to remain at the airport, sleeping on the floor and relying on emergency water supplies, illustrating the vulnerability of our transportation hubs to solar activity. The paralysis of the airports illustrates the close relationship between satellite signals and global transportation. Commercial aviation cannot operate safely without accurate positioning and communication systems, and the loss of these inputs forces a complete shutdown of the transit network, leaving millions of travelers stranded in foreign cities. In a modern cashless society, physical currency has been largely replaced by digital transactions. Most transactions are processed through cloud databases which verify accounts, authorize charges, and transfer balances. This system requires a continuous network connection between the point of sale, the merchant's bank, and the customer's financial institution. When the power grid and the communication networks fail, this digital transaction layer disappears. Suddenly, credit cards and mobile payment applications are useless. The plastic cards become worthless objects, unable to verify identity or process balances. Automated teller machines are dark and locked, preventing access to physical cash. The transaction system collapses into a cash-only economy, but because most people do not carry cash, the supply of currency is extremely limited. Stores cannot process sales, and gas stations cannot pump fuel without power for the pumps. For the international tourists, this represents a severe crisis. Their funds are held in foreign bank accounts, which cannot be accessed without network connections. They have no physical currency and their digital wallets are useless. They cannot buy food, secure lodging, or pay for transportation. The hospitality systems, including hotels and restaurants, require payment verification to provide services, and they are forced to turn away customers. The tourists are left with no financial resources in a parched environment, demonstrating how our reliance on digital banking can create a vulnerability during a systemic failure. The digital payment infrastructure relies on a network of servers that process transaction requests using secure protocols. When a credit card is swiped at a terminal, the merchant system transmits an authorization request to the card-issuing bank, verifying the account status and balance. This request must travel through local networks, internet service providers, and global databases to complete the transaction. The entire process takes less than 2 seconds, but it requires a continuous network connection and electrical power at every node along the path. When the power grid and the communication networks fail, this payment network is disabled. The merchant terminals are unpowered and the internet connections are offline, preventing any transaction verification. The plastic cards and digital wallets are useless, as there's no way to authorize a transaction or verify balances. The economy shifts immediately to cash, but the supply of physical currency is extremely limited. Automated teller machines are dark and locked, preventing people from accessing their bank accounts. The loss of the digital payment layer freezes commerce, as stores cannot sell goods and gas stations cannot pump fuel. The crisis is especially severe for international tourists who do not carry local currency and rely entirely on credit cards or mobile payments. They cannot purchase food, water, or transit tickets, and hotels cannot process their check-in requests without payment verification. The local businesses, facing resource scarcity, are forced to prioritize cash transactions, leaving the tourists with no financial resources. The hospitality systems collapse, and the tourists are left stranded in a cashless society that cannot recognize their wealth, demonstrating the vulnerability of a digital economy during a systemic failure. The collapse of the digital payment system highlights the fragility of our cashless economy. Without a continuous connection to cloud databases, our transactional tools are disabled, freezing local commerce and leaving the population with no financial resources to purchase basic supplies, demonstrating the vulnerability of our digital banking systems. The failure of the electrical grid triggers a secondary collapse in the logistics systems that support modern life. Our cities do not store food or water locally. They rely on a just-in-time delivery system, where trucks arrive daily to replenish supermarket shelves and warehouses distribute supplies in response to digital orders. This logistical system requires continuous communication, fuel, and data processing to manage inventory and route deliveries. Without power, this system stops immediately. Grocery stores cannot keep perishable food cold, and refrigeration units fail, leading to rapid spoilage. The automated inventory networks are offline, preventing warehouses from processing orders. Delivery trucks cannot refuel because the pumps require electricity to operate, and drivers cannot navigate without maps. Within 48 hours, the shelves of local supermarkets are empty, and the supply of food is exhausted. More critically, the water supply systems fail. Municipal water networks rely on electrical pumps to maintain pressure and distribute water through pipelines. When the pumps go dark, the pressure drops, and water ceases to flow to homes, hotels, and public facilities. High-rise buildings lose water pressure immediately, and sanitation systems fail. People are forced to search for alternative sources of water, collecting rain or queuing at natural springs. The logistical freeze turns the cities into zones of immediate resource scarcity, showing how quickly our survival parameters are altered when the grid is silenced. The distribution of food and water in modern cities is managed by automated logistics networks that operate on a just-in-time delivery model. Supermarkets do not store large inventories of goods locally. They rely on daily deliveries from central warehouses to replenish their shelves. This model reduces storage costs and improves efficiency, but it requires a continuous flow of data, fuel, and communication to coordinate the movement of delivery trucks and process orders. When the infrastructure fails, the distribution system stops. Without electricity, grocery stores cannot operate their checkout systems or maintain refrigeration, leading to the rapid spoilage of fresh food. The inventory databases are offline, preventing warehouses from processing shipments. Delivery trucks cannot refuel because the gas station pumps require electricity, and drivers cannot navigate the gridlocked streets. Within 48 hours, the shelves of local grocery stores are empty of basic supplies, and the supply of fresh food is exhausted. The population is left with only the food stored in their homes, creating immediate resource scarcity in high-density areas. The failure of the water supply is an even more critical threat. Municipal water networks use high-capacity electric pumps to maintain pressure and distribute water through underground pipelines from reservoirs to homes and businesses. When the power grid fails, the pumps shut down and the pressure in the system drops to zero. High-rise buildings and stadiums lose water immediately, and sanitation systems fail. People are forced to search for alternative sources of water, collecting rainwater or queuing at natural springs. The logistical freeze turns the cities into zones of immediate resource scarcity, showing how quickly our survival parameters are altered when the grid is silenced. The failure of the water and food distribution networks represents the ultimate phase of the logistical collapse. Our high-density cities cannot sustain themselves without a constant flow of resources, and the loss of power and communication immediately interrupts these pathways, creating immediate resource scarcity and challenging the survival of the population. Rebuilding the electrical infrastructure after a major geomagnetic storm is a long-term engineering challenge. The high-voltage transformers that form the backbone of the grid cannot be repaired quickly. They must be physically replaced. These transformers are massive structures, weighing hundreds of tons and containing miles of copper windings and specialized insulation. They are custom-built to match the voltage profiles of specific substations, and they are manufactured in only a few facilities worldwide. With a standard lead time of over 12 months, under normal conditions, the simultaneous loss of multiple transformers creates a bottleneck that the global manufacturing system cannot resolve quickly. The shipping of these massive units requires specialized rail cars and heavy transport vehicles, which may not have power to operate. The recovery process is delayed by the lack of electricity, creating a circular problem where the grid cannot be rebuilt without the energy required to manufacture and transport the replacement parts. Large regions of the host nations are left without electricity for months, forcing a return to a pre-industrial way of life. This scenario exposes the extreme vulnerability of our technological dependency. We have wrapped our planet in a thin, fragile layer of electronics, relying on satellites, cloud databases, and integrated power grids to manage our daily survival. We assume this layer is a permanent feature of our environment, but space weather reminds us that our systems are governed by the physical laws of the solar system. The sun, which provides the energy that supports life, can also silence our networks, reminding us of our position in the cosmic system. Understanding these limits is essential for building a resilient society, ensuring that the flame of our civilization can survive the solar winds of the future. The reconstruction of the power grid requires a coordinated effort that operates under severe resource constraints. The replacement of massive transformers is a physical task that cannot be accelerated easily, illustrating that the stability of our technological civilization is a temporary state that requires a resilient design to survive future solar storms. To understand the true scale of the cosmic threats that surround us, click on the video on your screen now. The signal is waiting.